Chapter 12. This is the Oxford University. It's some reason with the Indian Railway Press. The geometrical design of the track. The geometrical design of the railway track includes all the parameters will determine the effect of the geometry of the track. The permanent size of the gradient of the track include the grade consumption, rising gradient, falling gradient, the curve of the track, including horizontal, vertical curve, the transition curve, the sharpness of the curve in terms of degree of the curve of the cant, and super elevation of the curve, the alignment of the track, including the straight as well. The curved alignment is very important for the track. The proper geometric design in order to ensure the safe, smooth running of the train, maximum permissible speed, carrying the heaviest axle load, axle load of the train, very important, and sometimes also include parameters to consider while arriving at the geometrical design of the track. 12.1. Necessity of the geometrical design. The need for the proper geometrical design of the track arises because of the following consideration. To ensure the safe running of the train, achieve the maximum speed to carry the heavy axle loads, to avoid certain accident derailment, to affect the permanent wave, to ensure the track requires least maintenance because of the aesthetics. 12.2. The detail of the geometrical design of the track. Geometrical design of the track deals with the various aspects described in the following. Alignment of the railway track. The subject of the railway track alignment has been covered in Chapter 2. The detail regarding the curve of the various aspects has been discussed in Chapter 13. Gradients. The detail regarding the gradients are discussed in the following section. Gradients are provided with the negotiate the rise and fall of the level of the railway track. The raising the gradients, which for the track raise the direction of the movement of the traffic down the failed gradient is with the track loss of the valuation more direction of the movement of the track, which in the American is 1 to 100. The gradient is normally represented with the distance traveled, the rise of the fall of the unit. Some of the main gradients include with the percent rise of the fall. For example, if there's a rise of 1 meter in 400 millimeters, the gradient is 1 in 425 percent, is shown in Figure 12.1. Gradients are provided with to meet the following objectives: various stations of different elevation meet the natural contour of the ground to the extent possible to reduce the cost of the earthworks. The following so if the gradients are used the railways ruling gradient, the pusher to help with the gradient, moment, and gradients in station yards. 12.3.1. Ruling the gradient. Ruling gradient sheet with the gradient exists for the section that determines the maximum load that can be hauled with the locomotive on the section, while the design of the railway gradient on the section is not only the severity of the gradient, but also the level, the length, as well as the position with respect to the gradient on both sides has to be taken into consideration. More power, but the power of the locomotive to be put in service on the track that is also play an important role in taking the decision, as the locomotive should be adequate power to haul the entire load over the ruling of the gradient maximal permissible speed. Extra force is P required for the locomotive to pull the train, and the weight W on the gradient on the angle of the inclination of 0. So you have P equal to which pull weight of the train on 0, the sin angle or the tangent angle also 0, small similar weight times gradient. Indian railways do not specifically any fix of the rule gradient, owing the enormous variation topographical country traffic applying with the various routes, the speeding and the type of the locomotive the use in various sections. Gradually, following ruling gradients adopted the Indian rails where there is only one locomotive pulling the train, but plain terrain is 1 to 150 to 1 to 200 and 1 in 250. A hilly train is 1 in 100, 1 in 150. Only ruling gradient has been specified for a section. All the other gradients provided the section should be flatter with the ruling gradient after making due the compensation of the curvature. 12.3.2. The pusher and the helper gradient. In a hilly area, the rate of the rise of the train becomes very important, but the trying to reduce the length of the railway line. Therefore, sometimes the gradient is cheaper than the ruling gradient provided to reduce overall costs. Such situation when the locomotive is not adequate to pull the entire load with such extreme locomotive is required when the gradient is ensuring the section is steep. The necessity to use the engine of the pushing training is not known as pusher to help with the gradient. For example, the push gradient of the Budini-Barkaric section of the Central will aid the journey heavy lane railway section. 12.3.3. Momentum gradient. The momentum gradient is steeper than the ruling gradient, but it can be overcome with the train become with the momentum gap with the running on this section. The value of the failing gradient is sometimes found with the rising gradient. In such a situation, train coming down the failing gradient acquires the good speed momentum, which gives the additional kinetic energy the train allows it to negotiate gradient steeper than the ruling gradient. In section of the moment gradients, there are no obstacles provided in the form of the signals, etc., which may bring the train to the critical juncture. 12.3.4. The gradient of the station yards. When gradients in station yards are quite flat due to the following reasons: to prevent the standing of the vehicle for the rolling, moving away from the yard, but due to the combined effect of the gravity and the strong winds to reduce the additional resistive force required to start the locomotive to the extent possible. It may be mentioned that the general yards are not leveled completely. Certainly flat gradients are provided to ensure the good draining. The maximum gradient prescribed in the station yards on the Indian railways is 1 in 400, while the recommendation gradient is 1 in 1,000. 12.4. The grade compensation for the curve. The curve provides extra resistance to the movement of the train. As a result, the gradients are compensated with the following extent of the curve. The broad gauge track with a 0.4% of a degree of the 70 R, which is minimum. Meter gauge is 0.3 of a degree of this 52.5 R, which is minimum. Narrow grade is 0.10, 0.2 of a percent per degree of the 35 R, which is minimum. There are the radius, the curve of the meter of the gradient, and the curve of the portion of the section of the which shall be flattered with the rolling gradient because of the extra resistance over the curve. Sample 12.1. Find the steep of the gradient of the two curve of the broad gauge line with the ruling gradient of 1 in 200. The ruling gradient is 1 in 200 or 0.5%. Fifth of a percent. The compensating of the 2% curve 0.04 by 2 is 0.8%. Compensation grade is equals 0.5 minus 0.8 is 0.42%. 1 in 230 and 1 in 238. The cheapest gradient of the curve subtracting 1 through 238. The geometrical design of the railway track is the scientific method of laying the various components of the track ensure the safety of the trains will then run at the maximum permissible speed to carry the heavy axle load. The gradient is feature for the other geometrical design control for the hauling capacity of the engine. Other design features horizontal curve, super elevation, vertical curve. These are featured and discussed in this chapter. Alright, chapter 3, 13's curves and super elevations.